This is going to be an introduction to exponents. We're going to learn some of the basic rules, and then as we move on within this chapter, we'll see some more advanced rules dealing with exponents. But where we want to begin is by understanding what an exponent really means, being able to identify what bases and exponents are. Then we're going to talk about a rule when we multiply things that have the same base with different exponents. We'll talk about a rule for dividing when we have exponential expressions with the same base. We'll talk about a rule for raising exponential expressions to a power, and then we're going to kind of put all those rules together. So we're basically going to learn first what an exponent is, then we're going to learn 3 different rules that we'll have to apply individually as well as together. So we're going to start with the definition of the exponent. Basically, this too is an exponent. What it means is we're going to multiply the base 9 times itself 2 times. So 9 to the power of 2 has a base of 9 and exponent of 2. It means I write it as 9 times 9. If I did that multiplication out, I get 81. 7 to the power of 3 has a base of 7 and exponent of 3. It really means 7 times 7 times 7, which would be 343. Note the difference between these last 2 lines. In the top line, the negative is part of the base because the negative 2 is all in parentheses being raised to an exponent. As opposed to this bottom one just has 2 as the base. The negative is not affected by the 4th power. So really the reason for this is because of order of operations, either PEMDAS or please excuse my dear Aunt Sally, you may have heard it as. Within there, we do parentheses first, then exponents, then multiplication. This is really multiplication by -1. This is an exponent. Since exponent comes before multiplication, we do the 2 to the 4th power first, then apply the negative that's being multiplied by it. Whereas if I put these parentheses around, parentheses comes before exponents. So these parentheses tell me that not only does this 4 apply to the 2, it also applies to the negative that's within the parentheses. That's why this top one becomes -2 times -2 times -2 times -2, or in other words, everything in parentheses written 4 times being multiplied. This does have an effect on my final answer, where if I have the negative outside, I get -16. If I have the negative inside, I get +16. So the general idea here, base taken to an exponent, but make sure that you're aware of things like how these negatives are processed. So a natural number exponent tells us how many times its base is to be used as a factor. For any number x and any natural number n, x to the power of n is x times itself n times. In the exponential expression, x to the power of n, x is called the base, n is called the exponent. The entire expression is called the power of x. So really the nth power of x is what's being shown here. If an exponent is a natural number, it tells how many times its base is to be used as a factor. An exponent of 1 indicates that the base is to be used 1 time as a factor. Exponent of 2 indicates it to be used twice, and so on. We don't usually put the 1 exponent if it's not 2, 3, 4, something higher. It's understood to be 1 when you just have a variable. So here, x to the first you don't usually see, you would just see it written as x. But the same way there's an understood 1 in front to say we have 1x, there's an understood 1 in the power. If there is no exponent listed on a variable, you can assume it to be to the power of 1. Here we're seeing that you can write expressions such as y plus 1 to an exponent. There the base would be the whole thing, y plus 1. The exponent would be 2. If I'm squaring something like y plus 1, it really means I'm taking y plus 1 and multiplying it by y plus 1. That's going to come up in the 3rd or 4th unit of this class, where we're going to have to see how we would square things like this out. Note also, if -5s is all in parentheses being taken to the 3rd power, the entire thing, negative 5x, is being multiplied by itself 3 times. Here all I'm being asked to do is identify what is the base and what is the exponent. So in A, the base is 7, the exponent is 6. B is a little tricky. B has an extra term in it, specifically a coefficient, which is neither the base or the exponent. Only the x is being taken to the 3rd power. So here the base would be x, the exponent would be 3. I would not name the 4 as either part of the base or the exponent. Really, it's a coefficient that's going out front. That said, in something like D, where it's parentheses around it and the whole 2x is being taken to the 4th power, in this case the base is both the 2 and the x. So 2x is the base, 4 is the exponent. Whereas here, x is the base, 3 is the exponent. It would change if I put in parentheses. If there were parentheses that told me this 4 was also being taken to the 3rd power, then it would have a base of 4x instead of just a base of x. Part C just has a base of x. That negative isn't in parentheses, so it's more of a coefficient of negative 1. But really the base is x, the exponent is 5. So here they're going to walk us through it. To identify the base and exponent, we'll look for the exponent first. Then we'll say, what does this exponent apply to? So here the base is 7, the exponent is 6. Here the base is x, the exponent is 3. For C, the base is x, the exponent is 5. And for D, the base is 2x and the exponent is 4. We're now going to learn a rule for when we have the same base being multiplied with different exponents. And really they could also have the same exponent, the rule would still apply. But basically if I have x to the 2nd power times x to the 3rd power being multiplied, it's like saying this one is x times x, and this one is x times x times x. If we multiplied this, really we'd have the x being multiplied 5 times, which written in base exponent form would be x to the power of 5. So we started with x to the 2nd times x to the 3rd. By writing out the factors, we saw that became x to the 5th. Really, this leads us to a rule which says if you're multiplying same base, different exponents, or same exponent really, but as long as it's the same base being taken to an exponent, all I need to do is add the powers, and that's the new exponent on the same base. So the way that they write this formula is if I have x to the power of m times x to the power of n, the result is x to the power of m plus n. When we multiply two exponential expressions with the same base, we keep that base and add their exponents. So let's try and apply this rule to each of these expressions. If we apply it to the first one, the base is 9. They both are base 9. This one has exponent 5, this one has exponent 6. So the result from multiplication would still be base 9. Now to the power of 5 plus 6, 5 plus 6 would give me 11 in this case. For part B, it would be x to the 3rd times x to the 4th. That would be base x to the power of 3 plus 4 equals 7. Part C is a little more confusing just because there's 3 different ones to worry about. And this one I have to remember that even though there's not an exponent on it, it's an understood 1. I still do this the same way I did the ones above. Since they're all the same base, I just add all the exponents, this time adding 3 different exponents instead of 2. So here I would get 2 plus 4 is 6, plus 1 is 7. So my final answer would be y to the power of 7. When I look at part D, here I have 2 different letters. I'm going to need to keep those letters separate, but when I'm multiplying, I want to combine the exponents on the letters that look the same. So this C and this C have exponents 2 and 4. I would combine them and get overall base C to the power of 6. These D's have D to the 3rd, D to the 5th. I would combine them and get D to the power of 3 plus 5, or D to the 8th. So the final answer to this question is C to the 6th, D to the 8th. In general, when you're listing out letters, you want to make sure you put them in alphabetical order. That's why I'm putting the C first and the D second. In part E, notice there's plus signs between these letters. So really this whole a plus b is itself a base. A plus b to the fourth and a plus b to the third, when multiplied, end up as a plus b to the 4 plus 3, or a plus b to the 7. All of these problems are really just using our rule that when we multiply things with the same base, we combine their exponents. So this is walking through everything that we just did. When we do 9 to the 5th times 9 to the 6th, it becomes 9 to the 5 plus 6, or 9 to the 11th. When we take x to the 3rd times x to the 4th, it becomes x to the 3 plus 4, or x to the 7th. When we take y squared times y to the 4th times y, we add the 2 plus 4. Then we have to remember that really that last y is an understood y to the 1st. When we now add these exponents, 6 plus 1 gets us to the final answer, y to the 7th. Again, when we're worried about different variables, we can only multiply the things that have the same base. So here we can put the c's with the c's, the d's with the d's because they're being multiplied, but we can't put the c's and d's together. So this becomes c to the 2nd, c to the 4th, which combine to c to the 6th, and d to the 3rd, d to the 5th, which combine to d to the 8th. That's how I get my final answer, c to the 6th, d to the 8th. When I do the a plus b to the 4th and a plus b to the 3rd, again, the whole base is a plus b. This would be a different problem if it was a times b being taken to this certain power. We're going to learn that then you could distribute the powers and you would get something that was in terms of a and b separately. Here, because there's addition or subtraction between them, I cannot work like that where I have them as separate exponents. I have to keep it as one singular base, a plus b. Dividing exponential expressions is similar. The difference is instead of adding the two exponents when we multiply, we're going to subtract the two exponents when we divide. Specifically, we're going to take the one on top minus the one on bottom. So you can see here, if we think about it in terms of 4 to the 5th over 4 to the 2nd, there would be 1, 2, 3, 4, 5 4s on top. There would be 1, 2 4s on bottom. We'd cancel this 4 and this 4 with this 4 and this 4, and that would just leave me with 3 4s on top. So the final answer of 4 to the 5th over 4 to the 2nd is 4 to the 3rd. I can get that by multiplying these out, showing how many factors there are, or I can learn this rule. The rule says that if I take something with the same base written as a fraction, and on top it's x to the nth power, on bottom it's x to the nth power, then the result is x to the m minus n. Or in other words, power on top minus power on bottom. If we're asked to simplify these, note that it has to tell us there's no divisions by 0. Really, if, for instance, this x was 0, I'd get something divided by 0, which wouldn't allow me mathematically to do it. So this caveat, this idea that they cannot be 0, it just has to be said to make sure we're still mathematically allowed to do the steps that we're going to do. So here we have 20 to the 16th over 20 to the 9th. We keep the same base 20 and do the power on top minus the power on bottom. 16 minus 9 would leave me with 7. In part B, I have x to the 4th over x to the 3rd. That's going to become x to the 4 minus 3, power on top minus power on bottom, leaving me with x to the 1st, or just x. Here in part C, you'll notice there's two different bases that we have to keep separate. So for the a's, I have 3 on top and understood 1 on bottom. It becomes a to the 3 minus 1, or a to the 2nd power. For b's, I have b to the 8th over b to the 5th. It becomes b to the 8 minus 5, or b to the 3rd power. Step by step, we're going to look through how each of these occur. So 20 to the 16th over 20 to the 9th becomes 20 to the 16 minus 9, or 20 to the 7th. X to the 4th over x to the 3rd becomes x to the 4 minus 3, or just x. Finally, when we look at the one a cubed b to the 8th over ab to the 5th, we look at the a's separate and the b's separate. The a's is a 3 over 1, or 3 minus 1, which gives me 2. The b's is 8 over 5, or 8 minus 5, which gives me 3. So my final answer is a to the second power, b to the third power. It's important to pay close attention to the operation between the exponential and expressions and then use the appropriate rules. To add or subtract exponential expressions, they must be like terms. To multiply or divide, only the bases need to be the same. So what that's saying is I can't combine something like x squared plus x cubed. Since they're not the same variable, they're not the same base to the same exponent, I can't combine them. So something like 5x squared plus 5x cubed doesn't give me 10 of something. Whereas if I had 5x squared plus another 3x squared, since they're both the same variable to the same exponent, I could combine them. 5x squared plus 3x squared would give me 8x squared, because they are like terms. So here, this addition operation I cannot do. I can't do x squared plus x to the third, because they're not to the same exponent. As opposed to x to the fourth plus x to the fourth, same variable with the same exponent. One of these plus one more of them gives me a total of 2 x to the fourths. I can multiply when they have the same base, different exponents. X to the 7th times x to the third, I add 7 plus 3, and my result is x to the 10th. But if this had been x to the 7th plus x to the third, I would not be able to combine them. Finally, if I have this division, x to the 4th over x to the third, 4 minus 3 is 1, so it results in x to the first. The last rule that we're going to use before we put all the rules together at once is raising a power to a power. So this is when something already has an exponent being taken to a different new exponent. For instance, if I had x to the third to the fourth power, that would really be like saying I'm going to take x to the third and multiply it by itself 4 total times. If I did that, I would get x to the third times x to the third gives me 3 plus 3 is 6. X to the 6th times x to the third gives me 6 plus 3 is 9. X to the 9th times x to the third gives me 9 plus 3 is 12. You could also see it this way, where after writing it out, I can see I have 12 total x's. If I write out 4 different times x to the third. X to the third is really 3 x's, 3 x's, 3 x's, 3 x's, so I get a total of 12 x's. But the easier way to get there is to learn the rule. When you take a power to a power, the powers multiply. So if I have x to the third to the fourth, it becomes x to the 3 times 4, or x to the 12. Said in the same language that we've done the previous ones, if I have x to the power of m all being taken to the nth power, that gives me a result of x to the n times m power. So x to the n to the nth equals x to the mn. If we try and do this for 2 to the third to the 7th, we'd multiply 3 times 7 and get 2 to the 21st power. If I did it for z to the 8th to the 8th, I'd multiply 8 times 8 and get z to the 64th power. So there, 2 to the third to the 7th gives me 2 to the 3 times 7, or 2 to the 21st. When I take z to the 8th to the 8th, that gives me z to the 8 times 8, or z to the 64th. When we now put everything together, we have to use multiple rules at once. So for instance, if I try and take 2x to the third, that's the same thing as 2x times 2x times 2x. I could see that as 2 times 2 times 2, and x times x times x. So if I have that third power over a parentheses, 2 different things, I'm really applying that third power to each of the 2 things. 2 times 2 times 2 is really 2 to the third, or 8. X times x times x is really x to the third, which I can't simplify further. If I'm putting a power over a fraction, like 2 over x to the power of 3, that's really like writing 2 over x 3 times being multiplied by itself. On top, I get 2 times 2 times 2, which is really just 2 to the third power. On bottom, I get x times x times x, which is really just x to the third power. So what's actually happened here is a third power to a quotient like this just distributes, where it becomes the top to the third power and the bottom to the third power. Since I know how to do 2 times 2 times 2, I can change 2 to the third to 8 and get my final answer 8 over x to the third. So what the rule is really saying is that this exponent distributes when it's things being multiplied taken to that power. It's each of them individually being taken to the power and then multiplied. If it's a quotient being taken to a power, it's the top being taken to that power divided by the bottom being taken to that power. So if I was going to simplify these, for part A, I'd take 3 to the third power separately from c to the third power. For part B, I'd take x squared to the fifth separately from y to the third to the fifth. Since I'm multiplying, this would become x to the 5 times 2 is 10th, y to the 3 times 5 is 15th. Here I'm taking each individual part to the second power, so I'm taking negative 2 to the second, a to the third to the second, b to the first to the second. Negative 2 to the second would give me 4, a to the third to the second would give me 2 times 3 is 6, and b to the first to the second would give me 1 times 2 is 2. So my final answer here would be 4, a to the sixth, b to the second. Let's see these each done out. For the first one, when I take the third power to each thing, 3 to the third, c to the third, I can put in my calculator 3 to the third, and it'll tell me my final answer is really 27, c to the third. Same idea here, except I'm dealing only with variables. I'm going to distribute that fifth power to each of them. X squared to the fifth becomes x to the 10th, y to the third to the fifth becomes y to the 15th. Again, when I do it here for negative 2, a to the third b, each individual part gets taken to the second power. Remember that when this negative sign is attached here being taken to the second, negative times a negative gives me a positive. So that's why I end up with negative 2 times negative 2 gives me 4. A to the third to the second says 2 times 3 gives me 6. B to the understood first to the second tells me 1 times 2 equals 2. So here are the different rules that we learned, as well as a couple that are thrown in. Specifically, we just kind of touched on the idea that anything that doesn't have an exponent on it initially is understood to have an exponent of 1. We learned the product rule, what to do when we're multiplying two things with the same base. We add the exponents. We learned the quotient rule, or what to do when we're dividing two things with the same base. We take the power on top minus the power on bottom. We learned the power rule that basically said if you have something that already has an exponent being taken to another exponent, you multiply those two exponents to resolve it. For power of a product, I can distribute and say if x times y is being taken to the nth, that's the same thing as x individually being taken to the nth times y individually being taken to the nth. Same idea with a quotient. If it's x over y being taken to the nth, it's the same thing as x to the nth divided by y to the nth.